Good evening, dear participant, and welcome back in the seventh session of day 7 on survival analysis of our ongoing workshop on biostatistics from basic to advanced techniques. This workshop is jointly organized by Mathematical Thinking Foundation, India, and Baba Farid Group of Institution. Today, in this session, our resource person will be Dr. Mahaveer Singh Panwar, Associate Professor, DST-Centre for Interdisciplinary Mathematical Science, Banaras Hindu University, Varanasi, Uttar Pradesh, India. So before inviting him, I would like to have a brief introduction about him. And then after we will start our today's valuable session. He is an esteemed associate professor at the DST-Centre for Interdisciplinary Mathematical Science, Institute of Science, Banaras Hindu University, Varanasi. With a robust academic background, Dr. Panwar completed his PhD from BHU, focusing on Bayesian inferences for censored data from the Maxwell distribution. He has earned an MPhil and MSc from Chaudhry Charan Singh University, Meerut. His career has been marked as the progression through various academic positions, beginning as assistant professor at the Central University of Rajasthan and the Central University of Punjab before joining Banaras Hindu University. Dr. Panwar's research contributions are extensive with numerous publications in reputable journals and going on research projects. He has successfully guided several PhD scholars and is actively involved in interdisciplinary research projects, particularly in statistical modeling and disaster risk management. His dedication to academia and research is reflected in his sustainable body of work, which continues to impact the field of statistical science. He has vast experience in academia by these tools, R and Python also. And I hope that this today's session will be very informative, knowledgeable, and very hands-on to all the participants. In the previous lectures, we have introduced the basic foundation for the biostatic. And then after last 2 or 3 lectures, we start by using R plumbing and R studio. And today and in the coming sessions, we have a lot of practical sessions. So I request to all the participants also, if you can have your system with R and R studio, you can do parallelly all these things. So now I would like to invite our today's resource person, Dr. Mahaveer Singh Panwar. Welcome to in this session, dear professor. Now over to you. Yes. So also I request to all the participants, if you have any question or any query, you are permitted to unmute your mic during the session so that any kind of questions or query can be discussed during the, whenever you have any kind of question, you can put directly, and all the session is completely open for the discussion from beginning to the last. Thank you. Over to you, dear professor. Now you can unmute your mic.
Thank you, Dr. Meher. This will be great for me for the opportunity to discuss or deliver this talk with these participants. And as per my knowledge, what Professor Meher just messaged me, so we have to start from the very beginning and the very basic level from the survival analysis, and we will try to approach up to the Cox proportional general. At the same time, it is also, I will say, suggested that we are doing all these theoretical works with the help of, say, R programming. So again, in very beginning, I will thankful to Meherchand that he gives this opportunity to me, and I'm hopeful that next approx 2 hours you will will be engaged with this work. And as Dr. Meher suggested, if you have any doubt, any query, you just simply, I can't say it's interrupt. You just ask to me. I will stop, and first we will clear that. Then only we'll go to the next section. So in between, if you have any queries, so don't no need to be hesitate. You just ask at any time. So in this, as it is considered that it's a very basic or fundamental level of surveillance. So instead of preparing any PPT, I just try to find out is it possible to make with the help of simple whiteboard we can utilize in our this performance. So we can discuss at the same time. We can say make analysis or conclude the things or all the concepts. So one by one, we are just going with the say new whiteboard and just considering here. Okay, I think it is visible to all. Dr. Meher just once confirmed to me that,
yes, sir, visible, but look like a blank sheet.
Yeah, I will just start to write on that. I have just
Okay.
Okay,
Fine.
that. Good. Yeah. So the only purpose was that instead of just using some PPT and just we go through from first to last slide, my purpose is simply we just discuss one by one, point by point, all these things like lecture in the class, and then it will the responsibility of you all the participants that you just ask any query in between the program. Okay. So actually, I'm quite new for the Zoom. In general, we just go with the Google Meet. So if there will be some issues, I will ask you as well. So point is simply we are just going with, or as the topic is simply the survival analysis. Is here we are just the writing may be a little bit difficult to understand. Otherwise, so we are just going with survival analysis. Just believe me, my writing is better than this. It's just because of digital era. So point is, we are just discussing about the survival analysis overall the next 1 or 2 hours. And survival analysis is a little bit different from our upgradation of the basic things we just in the statistics. So we just make a basic change or modification in our variable. So in general, what we do, we consider a variable, say x. So x is a random variable. If it is a variable and it is random, just because of there is some probability or distribution is attached with that. So what we are doing, we are just making it a little bit improvisation in terms of survival. So survival is something like a person, an individual, or some units are survive up to some time. So time is actually the main factor or the variable of interest in survival. So in general, most of the standard books, what they use t as a random variable. So capital T is simply as a random variable, and most of the time it just emphasize about the time. So here simply we are just taking t as a random variable in place of x. We can consider x as well, but this it makes a little more emphasis on time. So t is a random variable, and overall study in surveillance is focused on simply time. So we are just going with time, and this is nothing else. Now this will be considered as a random variable. So here we are just study about this random variable. So point is what this random variable defines in terms of different experiments. So there are number of experiments. So in general, the term we used for a time is simply, or you have just said, so it is a failure time. So time is simply the failure time. So failure of something, most of the time we just say it is kind of if in terms of individuals or in terms of patients under a treatment, say like cancer. So failure may be kind of death, but in not all the cases it is simply death. Failure time means we are just studying an experiment. We are going towards a study. In that study, which whatever will be the variable of interest that actually come to the end, and it called as failure time. Say in a particular disease, we may consider once a patient just recover from that disease, and that time it just recovered from or just it's relieved from the hospital or some medical treatment, then we'll say it is a time of interest of all. That will be also called as failure time or response time or kind of dead time, elapsed time. So there are a number of different terms, but overall this T stands for the interest in a variable that belongs to somehow T. So in that way we are just going through in this lecture. So not all the time we are using the term failure time means death of something. But sometimes maybe say recovery of someone or just relieving from an hospital. Or sometimes it may be failure of some units, like if we are just experimenting in terms of electronics items like electric fan. So in that case, when the fan stop working, then we just say the failure time of that. Or sometimes we call this, it is a lifetime of a unit of lifetime of an individual. So both terms are somehow interchangeably utilized all over the survival theory or sometimes in the reliability theory. So here our focus is, if we will say, in the terms of survival analysis. So in survival analysis, once we just defining a variable, a random variable T, and if we'll say there are a few important key or characters which we utilize here. So if we just define a T variable as a random variable, then we are interested in, of course, in the very first, we just say FT, which is nothing else, simply the probability density function. So that we just done up to our graduation level or post-graduation level, that we are interested in a variable, and that variable is, if we just able to find out the probability density function for that variable, then it make easy for us to make any sum analysis or inference for that variable. So we just define ft for that variable t, a time variable. So it is as usual as we earlier used, or sometime we just go with the ft. This is nothing else, simply CDF, the survival cumulative distribution function. And then we are interested in, say somehow we simply say the ST. This is our survival function. We generally note that is a SF. SF is our survival function. So the whole theory will start from here. So it is nothing else, simply the survival function. Okay. At the same time, once we just define ST, there will be a term which is called an HT. And this term is the most important character of a variable in terms of surveillance. So this is nothing else, simply the hazard rate. Okay. And next, if we just define sometimes in place of small st, we just go with the capital ST, and this is equally the cumulative hazard rate. Cumulative hazard rate. So these are the basic term. If once we just define this, then only we can go with the other higher expressions or higher concepts in the surveillance. So these one by one are somehow, if we will say, are which simply says are connected to each other or can be defined from one to another. So point is, if we just define the T, then we just define the FT. FT is same, the probability density function is as for random variable as for the time variable. FT, as we just define in terms of CDF, cumulative distribution function, which is nothing else, the probability that T is less than or equal to T. But in terms of ST, what we are saying, ST just kind of complementary of this, and it is nothing else that the probability that T is greater than NT. In terms of CDF, we consider the probability of T less than or equal to T. If it is continuous, then we can consider equal to at the same time. So survival function, if the terms is nothing else, it is simply the probability. And this probability is equal to the probability that T is greater than T. That means a person in terms of time or lifetime, a person who's surviving, what will be the probability that he is surviving or she is surviving more than the time T. So somehow this is the survival function. And if we say in the real life, of course, most of the time we are interested in that what are the chances that a particular one will be survived more than a fixed time, a particular time. So that is our interest. Now, this can be, if you just say in terms of, this can be defined as like this. So ft is nothing else, probability that t is less than t. So you can define st as a 1 minus ft. So point is, why we are just writing this, that then if we have CDF, the cumulative distribution function, then you can go through the survival function with the help of that. So it is nothing that just simply in terms of reverse 1 minus something. So you just find the curve of that accordingly. So we will discuss about the curve at the same time. The point is, if you just try to find out what kind of a survival function curve will look like. So say I am just taking ST here and time point T. That was my point actually, to take the whiteboard instead of a PPT. That each and everything, whatever we discussion, we just discuss one by one. So this look like a proper lecture. The point is, what is happening as T is increasing, what is the probability? Probability of surviving something will be, in general, what we will say, as the time will increase, what happens with a particular, there will be some aging effects with an individual. And as the aging effect comes, that the chances will be lower. So it is a simply monotonically decreasing function. In terms of what? Just if we will say, I will define the two terms for here. Say what will happen if t is equal to 0 and what will happen if t is equal to infinite. So one thing, if we just go again, that t is a variable, of course it is a variable, and what is the chances that the range of this t will be, if I'm not wrong, that this t will be lies between 0 to infinite. A time is a variable here, and we can say that time cannot be negative. So it will may be greater than 0. So it will lie between 0 to infinite. So if time is lie between 0 to infinite, then what will be the chances of a person who is somehow defined on the behalf of t? Then if we just define what will be the value of s at the time point t is equal to 0. So in our experiment, what we are expecting or what we are prefixing, that any individual or any person will survive at the very initial phase of that experiment. So we are considering that this value will be 1. At any time point t is equal to 0. T is equal to 0 means the moment when we are just going to start our experiment. Okay, at that time we are expecting, we are fixing that that individual must be survived. So if must be survived, in that case the probability at that time of surviving will be 1. So at t is equal to 0, this is 1. But at t is equal to infinite, in particularly what we are saying, a very, very large time point, when the experiment is start, after that point, we are expecting at the end, infinite means at the large time point, means at the end, at the last of the experiment, it must be that each and every person must be dead at the time. The survival probability, the chances will be 0. So these are the two basic assumptions or the two basic conditions which we apply. So point is, now we can go with the, if I think this will be clear to everyone. The point is, at the time is equal to 0, the survival is 1. The experiment or individual must be survived. But at t is equal to infinite, each and everyone which is involved in an experiment, that individual will be reached to the failure time, and this will be probability of that will be 0. So point is, what will happen? So if now we can just plot this survival function over the time. So what we are expecting at t is equal to 0, in the beginning the probability of survival is 1. So survival function will be 1, and as the experiment at the time will pass, what will happen? This probability will be slowly will cover to the 0. As t tending to infinite, it must go to the 0. So that will be the simple function of our survival function. I think this will be clear to everyone. If you have any doubt, I'm again saying, if you have any query regarding this or any doubt with this, you just interrupt me, just stop me and ask about it. Okay. So fine, I'm just expecting that everyone is clear with that. So our survival function is simply a monotonically decreasing function. With time, it will either be constant, the survival chances will be constant, otherwise will decrease. There is no chances that it will increase over the time. Okay, so point is, so, and again, if I will say the 1 minus ft is here, so now anyone can be understand what will be the curve of ft. We will go through that in coding in some way. So what will be the curve of ft? So we will try to understand what is the nature of t. So can we identify the nature of t with the help of, say, this ft or CDF or survival function? So overall purpose of a survival is to identify the nature of t, the time points for a group of a sample, and how they are reacting, how we can visualize that. So in very first stage of this lecture, we will try to check that how these are working together. So once we are just identify the value of st, then we can approach to the hazard rate, which is ht. Actually, hazard rate is a core part of survival analysis. The hazard rate for an individual or a group is actually the movement, the force of movement that is somehow designing how the persons, how individuals are going to feel in upcoming time. So if we just define the hazard function, if we will say The expression is a little bit, so if we just define in terms of this, as our function is nothing else, just limit of delta t tending to 0. We just define this in that way. And then at the time, we just define the probability that t lies between t to t plus delta time t, given that a person or individual is survive up to the time, and the survival means that the t is greater than the, and then this will be divided by the delta t. Okay, so what we are doing in an experiment is that we are just fixing a delta t. Delta t is actually a arbitrary small, very small number, which is based on the experiment timings. It may be in minutes, it may be in hours, and it may be in days, months, or year. That kind of terms t is defined as per the experiment. So accordingly, we just define the delta t, and then we will try to expect what it is the if an individual, a person, is survive up to the time t. So under this condition, we just trying to find out the probability that what will be the probability. Then in actually next moment is he survive up to the time t, and delta t is a very small quantity. So in next moment he will survive under this condition. Then that is called as, sometimes we just define that as the conditional failure rate. So the hazard rate is sometimes called as simply the failure rate. Okay, so this is nothing else, simply the conditional failure rate. So this is the overall purpose of to calculate this. So as we just define the program PDF, we will define this will be simply limit of this first term. The conditional term is extended to this. If we just try to little bit solve this with the help of conditional probability term, the probability of A given B term. So what we will find? We will find say 1 upon delta t is here. So this will be nothing else that probability of A given B is probability that of A intersection B. You can see quite easily intersection B is nothing else, the common part of this, which is simply probability of this. So this is A intersection B part and divided by probability of B, and probability of B is nothing else t greater than t. Okay, so this is the expression. If we just try to solve this, so this is like, if we just say again saying, so this is like A, this will be termed as like B. So this is A given B. So A given B is simply, we can just calculate probability of A intersection B. Intersection B, if you just say there are, if we just define this, say here we have T, here we have some other term, T plus delta T, T plus delta T. Then the first A term define the condition between this, and the T greater than T condition define this. The common area is, of course, this one area is the common area. So intersection B is simply the T lies between this. So this is the probability of that, and this now can be defined as simply what it is. If we just simply say the limit of delta T tending to 0, 1 upon delta T, and probability is nothing else, as we know, is simply the PDF, probability density function. And if you just say in the denominator, if we will say it is probability of t greater than, less than or equal to, greater than or equal to t. So this is, we just simply define as t is here, or probability of t greater than b. The server function is here. So what we have to do to next page, let me check first. We just go to the next page. Spotlight. Any idea? I'm quite new with the Zoom actually, that's why I'm just facing some problem. Anybody, how we can just scroll this paper, or just give me some hint so I can. Dr. Meher, do you have an idea? Or we just get a new one? Anyone? Anyone in the audience have idea how we can just start here? Can we scroll this screen of the white Zoom? Spotlight. Okay. Anyone in the audience? Let me see the chat board.
Dear participant, if you have any question, you can unmute your mic, or either you can put your question in the chat box also.
Meher sir, is there an idea how we can just get to the next page in this whiteboard? Or
No,
just
sir.
scroll this down so I can just continue the same.
Sir, on the right hand side at the bottom, I think there is a plus
Plus.
sign. Please click there.
Okay, so it is just
Yeah.
going to the
This is the next page.
next page. By forwarding back to the next. Good. Okay, thank you, sir. Thank you. So another point is, if you just say in the previous one, what we have done, we just define all these things. We just at the hazard rate or hazard function was, if you will say, just define in the terms of HT is equal to FT by ST. So we will just start from here. So our hazard rate.
Hello, please.
Yes, please.
Okay, before you, my question is on the previous page. I'm trying to understand in terms of survival analysis, I'm trying to understand the role, the significance of the hazard rate, also known as the failure rate. I understand that in survival analysis, you're trying to calculate the time between observation and when an event occurs. So why are we talking about a failure rate? Are we saying that the event would fail to occur? Are we anticipating it to fail to occur? And then what implication does that have for the survival time?
Okay, good. I think I understand your point. The point is, if I just summarize the thing is, the point is in survival analysis, in terms of time, we are just defining the probability density function, we are defining the CDF, cumulative distribution function, we are defining the survival function. And if we just define the survival function, then what is the need to go to the hazard function? The actual point is here. And so what is the importance comes in the survival analysis about the hazard function. So all the time we are saying hazard function is the failure rate. So failure rate in the terms, we just take a simple example. So all the time what we are saying, I just try to identify this. The point is, if we have a survival function, just give me 1 or 2 minutes, I think we will make this clear. The point is, all the time we are defining our survival function will be look like this. Or my survival function for another patient or other particular may be this. Or survival function for particular patient or another patient will be this. So these are the 3 different curvatures of the survival function. Now, point is, if we just try to identify what is the reason behind that a survival function is quite peaked, quite flatter or moderate. So what making these changes in a survival function? So is there any factor behind that which is just responsible for that? But what force is there which is just trying to a survival function to be look like this? So in that terms, if we just say there is a function, yes, of course there is a function, and that function is hazard rate. So let me just try to identify how we just see this. So there is a very good example in general we just discuss with our students in the classes. So the point is, if I'm just discussing about the first is a hazard function which belongs to, of course, human beings. Say we just define the hazard function, a kind of hazard function which will look like this and that. Okay, so this is HT for particular person. So HT actually for us, the individuals, be it the human beings or anyone. So this is the hazard function which is defined over the time t. It will define the importance of hazard function which actually force the survival function will be look like that, or which actually define the times to be failed. So how it is working in human beings or in for us, what we say, when for a newborn, the failure chances is very high. For a newborn, the failure chances is very high. And that means in general, it is advised that the first 24 hours are very crucial for a newborn baby. Because of the immunity is very low, and there is higher chances to be say be caught by any disease or any virus. In that case, the chances of death is very high. So in that case, we say the hazard rate at that time in the first interval is very, very high. And this T just increase from say 0 to, we'll say, first 3 months. then say the healthcare persons just give the statement, okay, if it is just past 24 hours, you just take care for next 7 days. Then they will say that take care for the next 3 months, then take care for the next 6 months. So what is happening? But chances in the very first first 24 hours were very high, and then after those are somehow lowering down time by time, and up to a time point. So this time point is like I just say 12 year. So after 12 years or 15 years, what is the possibility? The possibility is that after that, the chances of a natural death is very low. Okay, or immunity of is at their peak. So there is no other virus is somehow not going to be the cause of failure of death of a person. So in that case, what we are saying, say up to some year, maybe say 45, up to the age group of 45, the hazard rate is very low and it is flat. Okay, very low hazard rate for any natural cause. So point is, in initial phase, because of immunity and all these things, we get a number of failures in the initial phase. The number of failures is very high because of what that is defined by in terms of hazard rate. So our survival function will be defined in other way. And then what will happen up to a year, 12 years to 45 years, this will be flatter. There is very low chances, the value of hazard rate is very low. So in that time, a natural death chance is very low. And after that, what will happen? There will be some aging effect to our organs, our lungs, hearts, kidney. There is some impact of our age. And after 45 years, again, what will happen? This hazard rate will increase and increase quite rapidly. Okay, and again, it will give the similar kind of chances of failure after the age of, say, we'll say after say 70 or 80. In the age group, the doctor again said that you have to make some conscious about your health and take care of many things, because right now the chances of death, a natural death, again becomes quite high. So in that term, we just define the hazard rate accordingly, the overall survival function going to behave. So that's what we are saying, that there is a direct relation between hazard rate and survival function. Okay, inversely related to that. So hazard rate is very high, the survival function will be very, means behave like it. And when survival function hazard rate is quite slow, the chances of survival will be large. So in that term, we just define the terms of hazard rate and survival function. So all these three things connectingly are making change in each other or depending in each other, or in somehow we say interrelated to each other. So here the term hazard rate. So point is, on the basis of hazard rate, we can simply define the survival function. And if we just, okay, I'm just make a curve, how it is important is that if we have hazard rate, if for an individual or for a group we have hazard rate, then on the behalf of that, we can go to the survival function. If we are going to the survival function, we can approach to the CDF and we can approach to the FT. So these are the formulas are already given. So point is, if generally what we start from, if in our statistical point of view, we just start from time and a variable, and then for that time we just define a PDF, then for that we define a CDF, then for that we define a survival, and then lastly we define a hazard function. But in terms of survival, actually we have an hazard function for some individuals. If we have hazard function, then we go to the survival function, we can define that. If we have survival, we can go CDF, we can go PDF. So these are the terms which are defined in general in terms of hazard. So actually hazard is the core behind the failure of each and every individual. So as our hazard function will be defined in literature, if you will say, there are a number of hazard functions, the form of hazard function. The simple form is hazard function is constant. Okay, over the time, if your hazard function HT is constant, then this will be look like this. But if it is constant, it not means that number of failures are defined in other way. So if in general, if you will say in case of exponential distribution, and if you will see if you will say the PDF of exponential distribution, which is positively skewed, actually highly positively skewed. And because of, I will just make this, you will try to understand or correlate how these functions are actually look like. Actually, we are used to see the PDF, probability density function. So in terms of this, for this particular hazard function, in which we are saying it is constant, it is defined for the exponential distribution. In exponential distribution, we know the exponential distribution PDF will be this. It is highly positively skewed distribution. And what it means that highly positively skewed, we are saying the frequency of failure in the initial phase is very, very high. Means most of the individuals are going to fail in this region, in the very first region. And then after this will be spread little low, and then after it will be look like this. So this is actually the nature of, if we'll see the probability density function of the exponential distribution. And then if we are just going to define the hazard rate for this, the hazard rate is constant for this particular distribution. So we have to understand what is happening actually behind that. It is saying this is constant, means in particular time point, out of number of say n, if there are some individuals which are going to failure, that ratio will be maintained over the time. Okay. So if there are 100 observations, out of that, if I just say 50 observations fail in very first hour, okay, then what we are saying, say there are a sample of 100 observations, okay. So out of 100 observations in very first hour, the 50 observations fail, 50 failure occur. So in that case, now what will happen the next 1 hour? Now we are expecting, because of hazard rate is constant, so this is 50, number of failures are 50, number of failure are 50. It means what is happening? Out of 150 fails. Now in next 1 hour, what will happen? Out of 50, those are survive in the first hour. On 25 will be failed. Half of that will again fail. So that's why we are saying the ratio maintained in this by the constant. It is half here, it is half again here. In the third hour, we are saying out of 20, half of them will again fail. Say I just simply say 13 will fail. Okay, and so on. Then 12 is remaining, then 6 will fail, then next hour the 6 and 3 will fail, and so on. So point is, in that way, half of the population or individuals in a samples are just failing in 1 hour repetition or in 1 hour interval. So that's why the cumulative hazard is looking like this, or PDF is looking like this. So what will happen? In the first 1 hour, out of 100, 50 observations will be failed here. In that next hour, in the second hour, out of 50, 25 observations will be failed here. In the next 3 hours, 12 observations will fail here, and so on. So that will be the pattern. So that pattern is defined behalf of this constant hazard rate condition. So I think it will be clear to everyone that what is the importance behind it, how it is regulating the whole things, regulating the survival function. Regulating survival function, it is regulating your time of failures. So hazard factor is the key characteristics in survival analysis. So all the time, our concern is nothing else, simply in the hazard rate. So once we are just able to find out the hazard rate, exact hazard rate, good approximation of hazard rate, then simply we can approach to the next, either survival study or in the say CDF or PDF, what kind of a study you are expecting, that can be done on the behalf of that. Okay, now point is, there may be another form of, one form is this, which this is simply called as bathtub hazard rate, which we human beings have just simply follow this pattern. In some particular cases, it may be constant, it may be linearly increasing, it may be any other curvature increasing, or it may be sometime decreasing as well, or sometime first increasing then decreasing. So there are number of if we'll say pattern are available in the constant in the hazard rate. So hazard rate are, as per the hazard rate, there will be accordingly the failure numbers. Okay, so we all the time, once we are just studying in the survival analysis, our concern of course is the time of failures of individuals, and that is governed by the hazard rate. So hazard rate is sometimes failure risk, or sometimes we just say risk in terms of risk, we just define that. So there are mortality rates, say in terms of we just go with the life tables. So there is a term of mortality rate that can be connected with the hazard rate, where we are also interested in the number of failures out of that. So these are the different things with we just approached surveillance. So if there is any doubt in this, you can just query here. Okay, good. So let me move to the next one. There are two expressions which are just somehow left from here. We just go with that. If in terms of survival, sometimes we are just not going with the derivation. We are just going with the right, simply the notations we just calculate it. It is 0 to t hx dx. So this is the another relationship with the help of that. If we just identify the hazard rate, then we can directly calculate the survival function. So survival function is nothing else simply exponential of minus of say simply hx dx. And say in case of say exponential, what we have just taken here, so it is lambda and t raised to the power minus of lambda x, okay, or lambda t. So whatever it is. So point is, if this is our exponential function and we just compare this function with the formula of this, so what we are saying here, say we can calculate survival function by some simply integrating from say t to infinite, or we can calculate fx in terms of that. So there are number of expressions we can define. So here, if we just go with the hx is again, will be the term e raised to the power this minus of lambda x. So we just compare this survival function is terms of here, and lambda is terms of here. Or if you just hint me, I will say. So if you just remember the previous expression says that ft is ht. The last expression was ht is nothing else simply ft and st. So here we can say that ft, generally we have the terms of ft, so this is ht and into the survival function, okay, the multiplication of here. And right now we just define that st can be defined as the term of exponential of minus of 0 1 to t hx dx. So this is the expression of ft. Now we can compare this directly from here. So any PDF function can be directly compared here, and it is comparable. If it's smooth, then we can directly calculate the value of ht. So here it is easy to calculate that ht is nothing else simply lambda in case of exponential distribution. And if you will talk about the survival function is nothing else simply exponential of minus of lambda x. So this is the basic way to calculate the hazard function. Otherwise, we have to get a simple expression. The survival function is nothing else, just integrate your ft from t to infinite. In that way, we can calculate that. At the same time, there is one more term, capital HT, we just defined earlier, the cumulative hazard rate. So this is nothing else, a accumulation of hazard rate. Accumulation of hazard rate is simply addition or add up, or cumulatively we are just going to add the hazard rate. So this is hx dx. So if we just accumulate, if we just add the hazard rate over the time, then this will define the cumulative hazard rate. So if you just see this expression is simply written here, okay, or in terms of this. So we can say survival function, we will just stop this basic here. The function is nothing else exponential of this whole term is simply hx or ht. So these are the relations between the PDF, the CDF, the survival function, the hazard function, and the cumulative hazard function. So all these 5-6 terms are somehow intercorrelated to each other. So these can be defined one by one on the basis of another. So our purpose or point here is to define that how we can correlate all these things. So if you will just say, I can give a basic example. Most of the time we're just trying to find out actually how all these are looking, how all these are matching in this. So we will just go with the R code after that. The next most important thing which actually define any distribution or any lifetime data is the sensor data. The point is, in general, what happens in another experiments, we have some observations x1, x2, and xn, but observations, say in terms of what the data in other, we simply say that we have an sample of size n and the observations are x1, x2, xn. That is simple in terms of that. But in a real life experiment of lifetime, that these terms will be defined as, we are switching to another things here, T1, T2, and say Tn. Okay, so it is in terms of X, we generally say, and all the time I just try to categorize the things different. So we can compare, actually we are used to with the X. Okay, X, any random experiment which is happening in the real world. But here we are particularly or specifically on the time. The point is, if time is specified, then we have to make the changes accordingly. According the experiments will be defined. So point is, what will happen that all the time these T1, T2, Tn, the failure of all individuals is not possible in real life, not all the time. So in that term, there is a very beautiful thing which is defined in the inference point of view, that is define a number of censoring schemes. So what is the censoring scheme? We are just approaching to this. If you have any doubt, any issue with the things which we have done in the last 2-3 slides, you can, if you have any query, just ask here, so we can smoothly approach to the next one. Anyone? Okay. Point is, so you can just stop me and we will go through this. The next point is, or the thing we are just, or next section is the censoring scheme. Censoring scheme the mostly utilized in your lifetime experiments and schemes. So we are not going in different various of censoring schemes are available in services. We are not going there. We are just getting 1 or 2 important censoring schemes. The purpose is that we just get the idea behind the censored observation in a real life or lifetime experiment. So point is, what is the idea behind this censoring? The point is, in lifetime experiment, what happened when we just going with the lifetime experiments? So in those experiments, or those experiments either very time taking. We generally say it is time consuming in terms of those. These are the real life possibilities consuming, or sometimes those are very costly. So we are just considering these 2 terms. Time consuming means you just started an experiment, you are interested to find out the lifetime of the patients, if we will say, and you just put n individual in the experiment. Okay, what you have done, you just take n patients, and with those n patients, you are just trying to find out their lifetime. And what happens, say, out of those n patients, few patients' lifetime is very, very large due to many reasons. So in that case, what you have to do, you have to wait until the last individual just not got to fail. But and then in the realistic problem, you don't have that much time that you will wait for the up to the last particular. So in that term, your experiment becomes so time consuming, so you cannot wait till the last failure. So means you have to censor your experiment in between your during your experiment. Okay, another thing may be you just planned an experiment, but in that experiment, the individual or unit behind which you are just going behind the lifetime, the cost behind that will be very, very high. So the failure of one will be cost a lot. The failure of another will cost a lot. So in that case, you cannot afford the cost of all failures. So in that case, you just fix a number. If that much failures will occur, we will just stop our experiment. So these 2 terms are just defined in terms of censoring. So these are the 2 basic censoring schemes. I'm again saying there is a number of censoring schemes are available, and a lot of research work have been done on censoring schemes. But here we are just discussing 2 very basic. These come under the right censoring schemes. So one is when the experiment is very, very time consuming, and the other is when it is very costly in terms of money. So in that case, if there are n individual in an experiment, then what we have to do? We cannot go up to the failure of all T1, T2, T2. So in first case, when it is time consuming, then what we have done, we call this, it is a type 1 censoring scheme. Simply, we just say it is a type 1 censoring scheme. So we will finish this within 5 minutes, and then we will go with the code. The point is, and the another one is type 2. Let me just make a comparison based study. So we have 2 censoring schemes. The first one is simply the type 1 and the second one is the type 2. In fact, type 1, what we are doing, we are taking a sensor time, kind of sensor time of experiment, and say this time is say C. Okay, so what we are doing, so there are some individuals, we are just taking it through this. Say T is our time point. There are some individual, these are the individuals. Say 1, 2, 3, 4, 5, 6, and say 7. So 7 individual in our experiment. So we just take an example. And we just fix a time point C here. So what the C will do, once any of the individuals come to this time point C, we will consider that point as a sensor. Say we'll say the lifetime of first individual is this. So it just failed any time point this. Then the failure time for second individual is this. So it failed at the time point this. But this third individual will survive up to the time say C. We just taking as a circle here. So what is the difference between this 1, 2, and 3? The point is first individual failure time is this. The second individual failure time is this. But for the third individual, the only information we have that individual survive up to the time point C. And after that, we have no other another information or additional information about him or her. So that is the point. So now what we can consider that we are just taking the exact failure study, and in that case there are say 2 individuals, we just got to up to that point. So in that case, what we can do, if we do not get the failure time for these 2 individuals, the third and the sixth one, so either we can consider them as missing observations, or we can utilize the information which we have. Means sometimes we just say something is better than nothing. The point is, what the information we have about the 3, we can consider that missing observation and remove from our experiment. That is the one policy. But another thing is that we know at least something about him or her. What it is, that particular was survive up to the time say C. That is the information we have. We don't know at what point is it going to fail, but at least we have the information that individual is survive up to the time. So, and the same for the 6th individual. So at least that kind of information we can utilize in our experiment. So in that data, what is the timing will be set, timing of first failure, timing of second failure, timing of third failure, and so on up to say timing of fourth failure and timing of first failure, exact failure. Then for the T6, the 6th individual failed at the survived up to the point 7, and the 7th individual also survived up to the time point C. So our data for time will be look like this. So T1 is actually we just consider the in ordered form, in sorted form. So T1 is the failure time which have the minimum time. So the person who failed very first, then the next one, the next one, the next one, and the next one. So out of 7, say we are considering say n is equal to 7 here. See, out of 7, the exact failure for T1, T2, T3, and T5, we got those values of time. But for 6th and 7th individual, the only information we have that particular person or individual survive up to the time C. So we just put a symbol of plus over there. And that is the data we have. That is the actual sample we have about that particular person, sample. So this is type 1 censoring scheme, where time is, the experiment is very time consuming. We cannot continue the time up to a large time scale. So what we have done, we just prefix a value C, and we will censor our experiment, kind of we stop our experiment once the experiment reach up to the time point C. If case all individual fails before this C, then we will get all failures. And if any one of them is surviving up to the C, we will stop our experiment and consider their lifetime survival time as C. So this is simply the type 1 censoring scheme, where time is consumed. But in second case, it is in a different perspective when we are saying the cost is quite high. So if n is equal to 7, what we are saying, say if m is equal to 3 individual failed, we will stop our experiment. because the failure of one will give a higher cost to the organization. So in that case, what we just decided, we just stop our experiment as we get the first three failures. So in that case, what is happening in actually in the real life scenario? Say we have some individual 1, 2, 3, 4, 5, 6, and 7. 4, 5, 6, and 7. So all just started. The first failed here. We are just taking the sorted terms. The second failure, and the third individual just failed here. Now rest of the individual, if you will see this, I just put them in the ordered form. The point is, all of this will be censored or experiment at that time point. All this will be censored over this time point, and this time point is nothing else, simply, if you will say T3. So first failure occurred at T1 time point, at second failure occurred at T2 time point, and as the third failure occurred, we just reached to our condition, we can bear only the failure of three particular. So as the three individual failure failed, then all other, say T4 is nothing else, T4 plus is nothing else, simply T3, and T5 plus is nothing else, simply T3, and so on. T6 is T3, T7 is T3. So in that case, our experiment just censored up to the time T. So in this case, what we have three exact failure, and rest of the observations are just censored up to that time. So these are the censoring schemes. There are a number of censoring schemes, again I'm saying, which are utilized. That may be, say, random censoring, that may be the interval censoring, there may be say progressive censoring, hybrid censoring. There are a number of censoring schemes are available in surveillance. All those are working, that they were known to them. But here we are just discussing the idea behind it. The idea is simply what happens in lifetime experiment. It is not possible for a researcher that he just continue with our experiment for a long time, or he or she will wait for the failure of all observations. So he adopts some processes, some designs or experiment in such a way that up to a time point or up to a number of failures, he just go, and as he achieved that number of that time or that failure, then he just stopped our experiment and consider the rest of the observations as censored at that case. So this is the basic idea behind the censoring scheme. So it is so realistic that in real life experiments, either in industries or in the healthcare or any field of a lifetime experiment, censoring schemes are highly utilized. So any doubt about that? Any doubt to anyone in this? Okay, good. Now let make some we just try to make some changes in our routine lecture. What we are going to do, let us see few things what we just studied in the last 1 hour, or just in the last hour, in terms of, if I will say, in terms of say coding in the. So I'm just stopping this to stop here, and what I'm trying to do, let me share. Let me share my. I'm just trying to share my. This is here, okay. Okay. So let me share my screen. Share a screen. Okay. Is this screen shared to someone will just confirm that? Anyone will please confirm that is it shared or not? Share screen, host disabled, attend share. Okay, Mayor sir, I think you have to give me the host disabled attendee share screen. Mayor sir, are you there? Just allow me to share this screen. Mahaveer sir. I'm audible now. I think I'm audible now. Yes, good.
Yes, sir.
Okay, great. The point is, I'm not actually able to share my screen. The host have to give me the permission. So I just want to share my R software, but this person is not picking my phone. So how that will be possible? Actually, my point was how we can generate the lifetime data in R1 and how it will be look like in terms of simple scatter plot, and we can identify that. And then after how we can go with the survival function or other functions, or even we can simply see the density functions over there. So there are a number of possibilities. So, and then how we deal with the sensor data and how sensor data is different from the complete sample. So that was my purpose. And if one is just able to this, then only I can be able to stream. So let me check one number. Okay. So what we can do, just suggest someone. Is this happened in earlier sessions or not? Yes, anyone can suggest me. Okay, till then time I'm just trying to talk to him. In between, anyone have any idea or any queries or any other questions regarding that? Not only just belong to what we have just studied. Other than that, you may ask to me or just write in the chat box. Okay. So that till that time, we just go with the next section. Then we'll come back with the same one. So in this try one time. And just join. Password. Let me try one more time. So, okay. I'm audible to all?
Yes, sir.
Okay. Point is here. We are going with the say T1, T2, and some time point, say Tn. So that kind of we simply say observations we collect in any experiment. So now point is what we can achieve here. Okay, the point is observations are T1 and say T2 and say up to T and the observation size. The point is what we have said that in observations, not all the time we get all those observations. So our sample is just simply somehow sensor say up to a sample size m instead of Tn. So if it is kind of we'll say type 2 sensor observation sometime, and sometime it may be it will say type 1 sensor where the observations are getting. The point is what we are just trying to find out in terms of a simple expression how the survival function is looking like. If we are interested to estimate this survival function, the point is how it will be look like. The survival function which we have earlier defined in the first hour is nothing as the probability that the t is greater than a kind of t. Okay, so we are interested to find out those observations which survives up to time t. So in simple probability terms, if we just go with that, what we have to do, we just calculate the survival function in some way that this will be nothing else, say n minus I. You will understand the very first way, say n. Or if I just write this is nothing else I by. So point is, what is survival function? The survival function is nothing else 1 minus probability that up to that time, if say I failure occurred out of an individual, okay, up to a certain time point t at which you are interested to find out the survival time, then what is happening? You are saying the I individuals already failure. So how many survive? Survival is n minus I. So actually you are interested the favorable cases, favorable is n minus I, and the total cases are n. So this is the formula. And we just solve this. This is nothing else 1 minus I by n. So 1 minus this is nothing else CDF. The number of individuals failed up to that time divided by total. So if we just calculate in some time points, then this ST is equal to 1 minus I1 is simply over estimate of survival function. So that is how, or that is in which we are interested to calculate. Okay. So I don't think there will be an issue with this. So simply just with the help of this, we can go with that. If you say what is n minus I, let me write down here. N minus I is in the first way the surviving number of persons surviving say longer than any time point t at which you are interested, or you may say write this ti kind of suffix here. So that is your expression. So point is in which we are interested to find out the estimate of survival function. In the very simplest way, the survival function can be estimated by simply s cap ti, which is nothing else than minus n by, or is equal to 1 minus I. That is your survival function. Okay. Now let make it little bit complicated. What will happen in the very first case? Maybe there are some tide observations. So let me write down here. Tide observation. Okay. we are actually trying to approach to the censored observation. So we just started from the, here the observations are exactly failure. At the same time, observations are exact failure. And in some way we'll say these are distinct error. Distinct error. So if observation exact failed and distinct, all observations are different. But there may be the possibility that few observations just, I will say, somehow tied. So in that case, let me assume that say T2 is equal to say T3 and is equal to T4. The point is, maybe two or more than two individuals just failed at the same time or kind of same day. So in that case, how you will calculate the value of survival function at this time point as T2? So means at that time, you have to calculate the survival at the failure of second. And of course, if those are equal, then this must be written in the form of this. Means a little bit tricky, if you will say. So point is, if in an experiment, two or more than two observation tied, means number of failure occurred at the same time point, say T2, T3, and T4, means three patients occurred the death or failure at the same time. And then their survival point will be the same. We don't know which one is the second, which one is the third. The simple term is both are equal. So in that case, that what we say at that point, how many individuals were surviving in the experiment? The expressions will be the same. Here you are taking distinct values one by one I, and now we are considering actually at this time point, whichever it is, you can consider this as T2, or we are interested to find out the estimate. So all the time points, the number will be n minus 4 by n. So actually at this time point, which are equal, we get n minus 4 by n as an estimate of our experiment. So let me take a data set, and for that data set, I will try to plan to give some expression. You will understand that. Say we have some time points. Say in the first, I just take a simple 4, 5, like 6, 8, 10, 12. So these are my failure time points. Okay. And if we consider the failure number of failures, so first fail at the 4, second fail at 5, third fail at 6, 8 fail at 4th, the 5th one, the 6th one. So these may be say simply in terms of hours. Okay. So first failure occurred at the 4th hour, then 5th hour, then 6th hour, then 8th hour, 10th hour. So accordingly, if you are interested to file out this escape, we will go with all this with the help of our coding. But okay, let's see. So the point will be out of 6, one failed at the time point 4. So what will be the escape? Escape can be calculated n minus n by. So out of 6, what happened? One failure. So this is nothing else, n minus 1. 6 minus 1 is simply 5 by 6. Then you will get 4 by 6. Then you will get 3 by 6, and so on. So this will be my survival function. But difference is that here the time points are actually different, will differ. So point is 1 hour, 2 hour, 3, 4, 5, 6, 7, 8, 7, 9, 10, 11, and 12. So that is our hours. So in that case, what is happening? Say we just started from 1. So there will be some value like 5 by 6 is around 0.8 or 0.8 something. So you will get first value somewhere here. So at the time point 4. So 4 is here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So these are time points. So the thing is, up to that point, 4 hour, the probability of that suddenly is step down at the point 4. Then at the point 5, it is step down again with some value 4 by 6. Then at 6, it is step down again with some value 3 by 6. Then it goes to up to 8. Then step down with probability something, and then it goes up to 10, then with some probability, and then it goes up to 12, and then so that kind of survival function you will get in the simple estimated values of your function on the behalf of time points, where time points are number one exactly defined and distinct with each other. So this is the example of the simple example of that kind of calculation. Okay, I will show all this with the help of say R coding, but okay, no problem. Let's see. Select. Good. Okay. Now next thing is we just go with the tide observations. So what will happen if the observations are tied? Your observations will be look like something like this: 4, first failure at 4, second at 5, next at 8 and 8. We got 3 failure at the time point 8. Then 10 and say 10 and 12. So if my observations are look like this, so here is a tie and again here is a tie. So what will be the difference between the first one and the second one? That will be the query. So actually I is 1, 2, 3, 4, 5, 6, 7, 8. So these are the failure. But once you are going in the survival point of way, then you have to calculate in the another way. So point is, in the first, you are saying at the time point 4, out of 8, 1 failed. So 7 survived. Sorry, 7, 8. Okay, good. Now in the next time point 5, out of 8, 6 survived. Okay. But then next time point, the failure at the time point 8 is 3 units. So that we are saying, in this case, we simply take n minus this 5. Up to 5 we are doing. 5 failed up to that time point. So second, third, and fourth. So this will be nothing else. 3 by 8. 3 by 8. Okay, just check this. Maybe there is some numerical problem. Then 2 failures again at that point. So just only surviving will be, we will say up to 7 it will fail. 1 by 8, 1 by 8, and then it will go to the 0. So that will be the expressions for the probability. And accordingly, our plot will change. So in this case, we will see how this will differ from that. So at the first point, there will be a short unit change after 4, then after 5, then there will be a 8 point, there will be a large step down. And accordingly in the 10, and then last will become the 0. So this curve will be slightly different from this tide observation curve. So there are 2 concepts we just consider in an experiment. Observations may be exactly failed or observed may be failed as per, if we will say, as per our tide observations. Now we are moving to the next thing actually in which we are interested. That was censored observation. Okay, again we have to go to the next one. It's going one by one. So if you have any query, please just ask to me so I can go forward. Okay, so let me delete this clear page and start with the next. Okay, so next thing in which we are actually interested is when data is censored, then what we will do? The exact formula will work, or we have to change our strategy. So in to cover this problem, actually the first time the Kaplan-Meier just define our term. So that is Kaplan. Okay. So what we are saying, we are going with the Kaplan. So actually Kaplan-Meier gave the concept what we can do to estimate the survival curve once the observations are censored in an experiment, which we have just understand what is the actually need of censored observations. Sometimes the observations are censored by default, but sometimes this is deliberately in our experiment, the experiment we conduct in our laboratory and all these things. And that time we forcefully or deliberately we just try to somehow arrange those experiments as per the censored scheme. So we can save our cost, we can save our time, and sometime both of them. So what it is doing, we are trying to find out the survival probability for each time. What we have done in the next case. So it has defined a functional form S cat t in another. We just calculated this for sensor data again and again. I'm showing. Say if ti is less than to a particular time point t, then this will be nothing else ni minus di, and whole is divided by the capital Ni. Okay, so this is our expression, and what it means, let me try to understand this. So how it will be defined, let me just give what is the meaning of these ti's. Of course, the same thing, the time of ith event. This is time of ith event. There is no problem with that. And the second one is Ni. Ni is, this is important actually, number of individual. This is nothing else, simply the number of individual. An important thing is at risk just before Ti. That is the important part. Just before Ti. So that makes this look like little different from the other. And the last one, the di we just calculate is the same, the number of events up to that time, is in which we are interested. So that is the expression for this. In first view, the experiments look like the same as we considered the earlier. That was n minus, if we just try to remind that, we just consider n minus I and whole is divided by n. That was the expression of survival function in case when all observations are exactly filled. But in this case, the expression is a little different. What he has done, he just find out Ni first. Point is, how many observations are survived up to that time point Ti, means those observations, those are survived, actually those are in the risk of failure. And then he is trying to calculate out of those Ni, how many just got filled after that time or during that time Ti. Then he just take the ratio of Ni minus Di by Ni. And then it is going to calculate the survival function. So this is a simple expression. With the behalf of that, we just calculate the survival function. So in this case, what the data will be look like this. Say your data is a first failure, then second failure, say third observation sensor, then fourth failure, fifth failure.
Sir, excuse me.
By chance,
We are not able to see your data.
one more time, sir. Can I hear you?
Sir, I can see only the whiteboard.
I just actually tried to share my screen of our software, but I think I'm not the host at the time, so unable to share that screen.
You would need to zoom in or zoom out. I experienced the same thing, but I noticed the scroll bar, the vertical scroll bar and the horizontal scroll bar. You may need to navigate them for you to see what's on the board.
Okay, I think now I'm able to. Do you want to continue? Yes, now it is providing the facilities here. Let me try one more time. Share what? This is screen. Now it is showing. Now this option is available, sir. Earlier I'm just trying at that time. I'm not able to share my screen. Okay, no issue. Let me finish this. Then I will go to the R software. Okay, still I have 20 minutes. I will try to cover that. Okay, sir.
Yes, sir.
Good. Existing whiteboard. Okay. It shows all the time. So what is it? All the time just try to share my whiteboard. It not show connection and I'm able to load this. Okay, let me start with my R software. I'm just sharing that and we will try to finish this. R software share. Just once confirm that you can see the R software.
Yes, we can see, sir.
Okay, good. Thank you. So let me try to finalize few things which we have just studied last 1.5 hour, and let's check how we will able to cover or not in the rest of the time. Okay. So here it's simply our software. I think you are all somehow aware to that. We will try to finalize the things. Let me display how the data can be shown if it is a lifetime data. So let me try to find out. Say it is a lifetime data. We are interested in that, and in that data, okay. What we have done. Say there are number of syntax available in the. We are just going to the particular one. Say we are saying the data one is equal to. We are simply say we just generated some data, our exponential distribution with a size 100 and some parameter value say 0.5. So this is nothing else in data. So what we can consider these values like lifetime of some individuals, of 100 individuals. So I just consider in that way. Okay, you just take the value of say 0.1. Okay. So values will look like this. So you can just change the values. My point was, okay, just go through the very first few slides what we have done. So if this is the data and I just plot this data, how it will look like? I just going with data 1 and here is the plot. Okay. Just identify the observations. So what we are trying to do is try to understand. We are planning to see our lifetime data, simply say called as EDX, correlated data analysis, then how your observations will be look like. So we can understand that because observations are generating from exponential data, you can see the cursor here. So point is which is highly positively skewed, and if it is highly positively skewed, in that case, all observations are near to flow. If near to flow means around to 0. Okay. So that particular characteristics is actually making this is a highly positively skewed. Observations are just near to 0. Or if you are a little bit aware from other distribution, so let me plot. I just plot R norm. Okay, normal distribution. We all are aware about that. We just consider say 0 and 5. Let me plot this data. We just try to find out how observations are distributed in this case, in the previous case, and in this particular case. So what is happening here? So observations are distributed near to 0. As we know, the normal distribution or Gaussian distribution is symmetric distribution, and it's symmetric about mean. And the mean is 0. So most of the observations are near to 0 and distributed over 0 symmetrically. Okay. So that is simple scatter plot. So in the same way, I'm just trying to find out how my exponential distribution will be look like. So these the scatter plot for the exponential distribution. So you will see the most of the observations are on the floor near to 0. And few observations are scattered or dispersed over the values over say 60 or 50. The point is just because of my data is positive. So in case there are some other distributions for which we can just identify the distribution is positively skewed or distribution is negatively skewed or it is symmetrically skewed. So in that way, we can define over say lifetimes. So these are actually nothing else lifetime. If we just consider that observations are following the lifetime of following exponential distribution, so those will look like this. So we can just see these observations or just visualize these observations. Somehow we can identify which kind of distribution will be better for us. Okay. So we can identify it is positively skewed, it is symmetric or negatively skewed. And if you are interested to see some kind of plot, say let's go with the density plot of this, say data 1. So density plot is somehow. So we just taking the bandwidth, we just regulate this will look like exponential distribution. Okay. So just due to approximation, it is like that. The same if you will do with the normal distribution, that will look like symmetry. So my point is what I'm trying to say, that all these dealing which we have done in simple observations or X observations, all those things can also be targeted, can also be identified with the help of a simple plotting method. And then we are going some other methods. Okay. So now time is quite short right now. So we are just going, I just find out a data and we are just going with that. The data is quite easily available. Lot of examples are also available for this data. And I just particularly choose this data. Then after this, you can again just go to the Google in our software and you find out that lung data is available in the survival package. And you can do some other calculation as well for that. So first of all, you have to install survival package. I already installed it. Then you get the survival library, that is simply survival. So lung data is available over here. If you just try to identify this data will look like this. Okay. So in this data, there are a number of, if we'll say variables are available. So let me just go to the help where I just open this lung data. If you just try to understand what they are doing with this data it is simply survival in patients with advanced lung cancer from the North Central Cancer Treatment Group. Performance score rate, how well the patients can perform usual daily activities. So this data is simply take some variables like institute code, this is not open interest at the time. We have survival time in days, that is our actually lifetime. Okay, let's say try to understand the survival time is in that terms is kind of lifetime. Then okay, you can see here there is censoring status. 1 means it is censored and 2 means it is dead, an individual is dead. So here you can see the status. So status variable is here and you can see in this the first fail person is dead, second is dead, the third one is surviving up to that time. Okay, in days, the third person is surviving up to the 1010 days. Then the fourth is 2, he died after 210 days. The third one is fifth one is dead after 800 days. So that kind of data we have. Some other things are also available for that data, which is we are not going to utilize. That is age, the sex of that particular patient, either he's male or she is female, and pH echo. We will consider this later. So now we just go with the same thing. Okay. So this is our data. What we are trying to do in Kaplan-Meier. So there is in survival package already a surfit command is available. So what you have to do, you have to consider the serve syntax over there. So it will consider your time, and at the same time it will consider the status. What is the status? Status is that it's censored or dead observations are available in your data. So in that case, we know that status is one with the censored observation. So that's why this surfit command is used for Kaplan-Meier estimation process. So this is well known for the statistician that we generally in class we just give this example. So for our data is lung data. So 3 things you have to define in surfit. First, the data for the time which you are studying, and then second one is the data. And if it is censored, then status will go with the 1. Okay. So here we just run this program. Good. And then we are actually interested in the plot of with this Kaplan-Meier fit. how it is fitting this particular data. So here is the graph for this particular data set. The similar kind of survival fit which we have done earlier, say on the whiteboard, the same kind of survival curve is here, estimated survival curve is here. But the point is, in this particular data, observations are censored that cannot be calculated in the direct way. So it is utilizing that improvised function of given by Kaplan-Meier for the sensor data, and then he just calculated this. At the same time, the advantage is that what he has done, that it gave the boundary as well, the 95 confidence interval, the dotted line. So this is your solid line is your the survival fit, and the dotted lines are simply the 95 lower and upper confidence. Yeah, they give some more. Okay, so they also break actually on the behalf of their sex. What is the differences with the male and female data? Okay, so in that way they just define two survival curves. Okay, if we are interested, is the gender is affecting the survival pattern of those individuals in that group. So what he has done, he just break the data in two parts, one for males and one for females, and then he just fit the Kaplan-Meier estimates. And here for the red one, the line shows the for the females, and this blue line for the male. So these are the estimated values of the males and females. So here anyone can be, if we will say, interpret or conclude that as this red line is actually all over the time points are on the upper side of the blue one, so means survival chances or probability in terms of this survival function estimated curve, you can say the females are somehow performing better in terms of lung cancer data of that particular state. So does anyone have any doubt regarding this, either in terms of curve or code or concept? If you have any doubt regarding this, I think this will be better. Okay, so in that case, we are just approaching to our last expression. Actually, that was our solely purpose for this this lecture. Again, we are going with the whiteboard. Let's see how it will work. It's taking some time. Okay, 10 minutes are available. It's quite short for that, but let me try to at least we get some idea about it. Okay, the point is sometimes what happens, we are interested in another way to study in between two groups. So as we just said in the male female data, we are interested to find out is there are one group is performing better than the others, or like so many things. And the point is, only time is not only the factor. So there are some other things are also there that can help to inference about the time. Okay, let me see how it will be helpful. Then what we are saying, we are considering a data in which we are going. So simply we are defining the Cox proportional hazard model. Okay. So in that we are saying till now we have the time, and we are studying till now the last 1.5 hours about the time point. But what we are saying, there are some other covariates are available. Those actually help us to estimate or give some inference about this time. So like we just leave in the previous example, say gender has some impact on time. Okay, so the point is there may be gender may be a factor, there may be age somehow a factor. Okay, a patient of say young age may give the better chance of improving or survival in respect to the older age person. And there may be another, say education is one of that. He can care in better way, or many more things. Diets may be helpful, or physical activity in some cases. So there are number of factors, or we will say simply the covariate. Those helps or those have impacts on your time. So person with different gender, different ages, and different educations have different kind of server function. But once we consider all those in a simple group, then we have to consider those also, because they are directly impacting the time. So point is, we need kind of model. In that model, all these covariates also included, and then after we are going to estimate the t. Okay, so this will be possible then only when our data structure will be looked like this. So what is the data structure actually is? If we say we have the time point for the jth person or jth individual, we have del j, which is showing that particular is censored or not, and at the same time we have some zt kind of. So this is a new expression which is included in this data set. So let's say this is x. X is the data set for the jth individual, and then we are interested to find out. So we have the time points as usual. We have delta j, so del j, which show that either it is sensor or not. So del j will take value either 1. So this will be either 1 or 0. So you can define if 0 is the case of censored, and this is the case of failure. Then some ZJT is over there, which is actually we are saying is a covariate. So let me define this. So ZJT is a covariate or a vector of covariate. In general term, we define this. So this may be ZJ1, the first factor, then ZJ2, the second factor, and so on. So that may be P such factor. What these P factors are? So like this is age. So this is again we are taking gender, and so on. Okay, so these are the P different factors or covariates which are associated with an individuals, or those are affecting or giving some impact on time, and according the survival time will change. So that's why in study of this T, it becomes necessary that we utilize those particular cofactors. What will be the advantage in terms of advantage? We say in that time the inference of this T will be say less biased. Okay, and at the same time it may be, we can say it will be more precise. With the help of these covariates, we can able to inference about T, but with more precise way, less biased way. Okay. Now there are some possibilities that this Z may be time dependent or time independent. So in this, which considered by the Cox proportional hazard model, they considered in the very first way that simply we are considering, if I will say, time independent. Okay, so these are time invariant, no time variant. If your covariates are changing or have the impact of time of experiment, not lifetime, experiment time, in that case they are time variant. But if it is, say, if we consider gender, so gender will be the same over the time. So that means it is invariant. At the same time, we consider age. Age is actually age of diagnosis. So age of diagnosis going to be same over the years. Okay, at what age he just diagnosed the particular disease, then this will be invariant. Or sometime if we consider a variable like blood pressure, so in that case blood pressure is going to be changed over the time. At different time points, you just say the blood pressure will be different. So this will be time variant covariate at the same. So in very first, what we are saying, we just consider. Okay. So in that case, what we are saying, we are just going with the simply Z JT will be simply Z. So there will be no T involved actually. Over they are not dependent on T. So you have that kind of covariate, say T covariate. And we are interested now to utilize these covariate in our model. And as we said earlier, that hazard rate is the most important character of a survival point of view. So if we define a survival function which is based on Z, so that will be our model. We are interested in the hazard of T, but this hazard is somehow impactful of Z. So as for the Z or conditioned over Z, what will be the hazard rate? So that is our. So the folks have defined in 1972 that this can be defined in terms of B prime beta prime Z. So this will be our hazard function. Hazard function condition over Z is nothing else H naught T and G beta prime Z. So this is our baseline. This is called as baseline hazard. Okay, baseline hazard. And that is our function actually in which we are interested. So it is a known function. Generally, a known function, we define this function. And the parameter involved, this beta is our parameters. So once we are just able to find out these parameters or estimate these parameters, then we can define this whole structure. How it, the point is, okay, it is hazard which is defined the base of that. Then why we are saying it is proportional hazard model? What is the meaning of that? Actually, what it is saying, the idea behind was that if say two individuals have covariates Z and Z star, okay, one individual has Z and another has Z star, and we are just trying to identify which one is performing better than others, or and so on. So the point is, he just simply take the sorry. So what is the stake? He simply take HTZ, the proportion is HT for Z star. So for these two covariates, he's just going with that, and you will see. So this will be for the first one, it will be G beta prime Z. If you will say, we can define G first, H naught T and G beta prime Z star. So of course, overall, we have the two expression, the Z beta prime Z, which is solely, if you just try to find out this, there is no such factor of T in this case. These are only based on Z, the covariate. So actually it is constant over there over time. So simply our function becomes, that's why we are saying it is a proportional hazard function. And if we just consider any particular form of this, the most utilized form of this Z beta prime is actually exponential of beta prime. So this is the mostly utilized expression for this. Exponential of beta prime. So this G just reduced by this. So in that case, if we utilize this here, so it will become exponential of beta prime, and or in terms of sum, if you try to write this, beta k and zk minus zk star. Okay, k is varying from 1 to p for all this. So that kind of expression we will find out this. So because of in this ratio, there is no terms of baseline hazard, no terms of T, so it becomes constant. And this is actually the risk, the factor behind that. And we can calculate this on the basis of that. So if it is interested to find out the likelihood, I'm not going the theory in the likelihood. We are just, okay. Let me just define the likelihood. The likelihood function will be simply written as the product of, we will define at which I we are interested, and the exponential of simply beta say prime Zi, and the whole is divided by sum over J belongs to, this is again a risk factor which we are interested is, and exponential of beta T and Z. So that will the term we will define for this likelihood is based on, there is no role of baseline hazard here. It is completely based on the covariate function. So that's why we simply call this partial likelihood. This is not a full likelihood. So there is no need of to find out that. And on the basis of our data, we are just simply interested to find out the estimate of beta. And beta, that is nothing else than with beta 1, beta 2, and so on. So beta. So this is the overall purpose of the whole estimate. The RTI becomes important here. This is the risk set at time t. The same thing we just in the earlier section. The RTI is, this is the important part. This is risk factor. With this, we were just going to conclude this. Risk factor, sorry, not factor, set. So this is simply the risk set at time t. Okay. And if you will see, we're just going with the same. Continue with this. We are same data. Actually, that's why I just considered that data. Okay. Lung. We are just also going to implement the same thing on the data. Lung data. It is very simply we just define there is well-defined commands are available in the software. So what they have done? So simply there is, we just consider the library section, we just take our data, add it simply, then we just define the Cox model. Cox model, proportional hazard model is again in the same way. The only difference is what we have done, we add some covariates. If you are able to see in the previous model, Kaplan-Meier, we are not utilizing them, but here we just add age as a factor, sex as a factor, pH equals as a factor. And what is pH? The most important one is post performance of the lung cancer patient. It is actually showing this on the scale based performance. If it is 0, then he is doing good. It is 1 that he can actually walk. Second, he on bed, but less than half of the day. Then 3 is on the bed. Then there are some categorization of the patient at what level they are suffering at that time. So these 3 factors consider the Cox model. These are like Z over here. So this is the Cox model, and here are the summary. Let me see the plot first. So this is the plot of that data after considering the factors age, sex, and pH dot research. In the previous, we have the observations. I think this is the survey. Okay. So this is the plot in the earlier case, and this is the case after that. Okay. The point is, what we will see in the summary that will give you whole calculations behind that. What it has done, if you will just see quickly, this is our model. Observations are 2027, only 164 observations, and rest are censored. And these are the coefficients or estimates in which we are interested. For age, it is 1 point this. For sex, it is 0.57, and for pH, it is 1.59. And these are following all the conditions of testing and all these things. So the point is, we just calculated the beta 1, beta 2 estimates. For all those, we are also calculated the lower end of confidence intervals and rest of the things, standard error and all these things. So means if we have data, and for that particular data, if we are interested to add some covariates, and it is censored at the same time, and those covariates are not at such time dependent invariant, in that case we can go with the Cox proportion hazard model directly. So I think this is enough for today, and hopefully you will just get at least some idea about the surveillance, and rest of the thing you will understand by the self-estimate. This is for my side. Dr. Mehta.
Dear participant, any question from your side? If you want to ask, please feel free. You can unmute your mic, or either you can put your question in the chat box if you have. Okay, Dr. Biswadeep, Sonia Malik ma'am, Jitendra Kumar, anyone please? Pooja Sharma. If anyone have any question. Okay, I think there is no more question. The session was really very interactive and hands-on also. Okay. So thank you to all. And as we come to the close of this enlightening session on survival analysis, I want to extend our heartfelt thanks to Dr. Mahaveer Singh Panwar for delivering such a comprehensive and insightful presentation. Dr. Panwar's expertise has greatly enhanced our understanding of survival analysis from the foundation principles to advanced techniques and its applications in various fields. His ability to demystify complex concepts and share real-world examples has been truly invaluable. So once again, thank you, dear Professor, for your valuable time. And tomorrow is also we have Dr. Panwar, and I hope that tomorrow we the topic which we are going to cover. Just 1 minute. So I request to all the participants, please join the session in well time so that we can have some more time. Yeah. So
Okay.
tomorrow we will come to
Longitudinal.
yeah, longitudinal data analysis. So this is also very important to all the participants. Thank you to all once again and good night. The session is now over. Tomorrow we will join at the same time.
Thank you. Thank you, sir. And thank you all the participants.
For your time.
Let's meet tomorrow.
Yeah, tomorrow at the same time. Thank you very much.